Phobos Deimos exploration seminars, and we're lucky to have Mike Gernhardt here to talk with. Mike started his career as a professional deep-sea diver and in oil field construction, and logged something like 700 deep-sea dives, and decided to take a massive change in career and also a massive pay cut, and got into science, and became an astronaut. Got his PhD in bioengineering in 1991. Took 4 flights on the space shuttle, logged 43 days in space, almost 24 hours of spacewalks. And so he's been in a variety of inhospitable media. And what's particularly useful for this course is that he runs the human architecture team for future exploration of Phobos and Deimos. And so, Mike, please take it away.
Okay, thanks, Dan, and good afternoon, everyone. So I'm going to step through which involved a really great, dedicated, talented team across the agency. These are some of the names. I don't have time to call them all out, but very dedicated and done an incredible amount of work. And as usually I try to do in these studies, we actually attack this study like we're the flight crew and the flight control team and the engineers that are actually doing the real mission. So try to add a sense of operational reality to it beyond just sort of the view graphs and so forth. So I'm going to kind of just step through all of this. I take it you guys are all scientists, so I'm not going to bore you with the details of Phobos and Deimos. You guys know more about that than I do. In way of introduction, though, Mars moons are interesting scientifically, and they potentially offer engineering, operational, and public engagement benefits that could really enhance the subsequent Mars surface operations. And with that statement, I'll also make the point that as we started this, I was nearly militant about not doing things that were Phobos unique, that didn't add to Mars surface, because I see this as a step on the way to Mars surface, but not as an either or, and so that's part of the theme that permeates all this. But so the Mars moons are interesting in themselves, also likely provide insights into the evolution of Mars. Are they're moons of Mars? They're possibly captured asteroids. They likely contain Mars surface materials. Probably some materials from the asteroid belt, and then they offer near zero latency teleoperations of Mars surface assets. So potentially Phobos Deimos would provide an affordable first step toward eventual Mars surface operations. Phobos also provides significant radiation protection. Phobos and Deimos are interesting exploration destinations in themselves. With the current imagery, we know that Phobos is interesting with the craters and the fissures and the monoliths. And it was also the driving transportation case, and therefore it was the focus of this study. We are presently formulating a precursor mission that will look at both moons. So when we started this study, and let me know if the slides are going well, but when we started this study, I wanted to get an intuitive feel of what the gravity level was. And the gravity is 0.0057 meters per second squared. And so this slide just shows how much a crew member in a suit would weigh, a little over a quarter of a pound. The space exploration vehicle that I'll talk about in a few minutes would weigh about 7 pounds, 8 pounds on Phobos. 15-ton habitat would weigh about 20 pounds, and a 50,000-pound lander would weigh about 65 pounds. And if a human, Michael Jordan-style human, jumped at 2 meters per second, which is about as good a jump as a human can do, in a suit on Earth Moon, you would go up about 1.2 meters. The time flight would be 2.5 seconds. And the picture there is John Young basically doing that. And then on Phobos, if you did the same jump, you would go up 350 meters with a nearly 12-minute round-trip time. And on Deimos, nearly twice that. So there is gravity, and it actually provides an interesting amount of gravity to try to make that gravity work for us and not against us. So when we started this study, the first thing I'll say is that we only looked at conjunction class missions, And the overall architecture was to pre-deploy assets to Phobos, and then the crew would arrive in high Mars orbit with the crew transit vehicle, and then we would taxi over to Phobos, and I'll talk about that more later. But in terms of the overall trade space, the destinations, we looked at Phobos, Deimos, and both. Transportation was conjunction class, pretty much exclusively. We looked a little bit at free return trajectories, and that's work that I think is worth looking at more in the future. It offers some interesting savings in terms of prop and delta V, introduces some other challenges with respect to the reliability of making the intercepts and so forth. As far as the pre-stage assets, we looked at none, a Mars-Moon habitat, and then a Mars-Moon habitat plus pressurized excursion vehicles that I'll talk about more later. And then as far as the habitat, we looked at surface, both static and mobile habitats, and then we looked at various orbits from the L1 point. We looked at L4, L5, and then DROs, that's distant retrograde orbits. And then as far as what I call work systems or exploration work systems, we looked at jetpacks, unpressurized excursion vehicles equivalent to like an Apollo rover, and then different classes of pressurized excursion vehicles that range from the Space Exploration Vehicle class, which is based on the lunar rover work that I did, and then Mars Lander or Mars Ascent Stage class. One of the big benefits of being on Phobos' surface is the radiation protection that you get. And this is a bit of an eyesore, so I won't read all of this, but basically we look at different launch dates, and then we ran the Alteris model, which is the model that the Langley team uses and the JSC team uses. And what we have with different locations is if we have a habitat on Phobos' surface in a 10-degree crater rim, we could potentially reduce the total GCR radiation dose on the humans by up to 34%, and that includes the whole mission. So that's the outbound trip, that's the hundreds of days at Phobos, and then the return trip. Once you get into even a 20-kilometer DRO, that radiation protection falls off. And then at L1 and L4 and so forth, you basically don't get much radiation protection. So there's a big benefit of having the crew on the surface to take advantage of that radiation protection. When we started the program, we built on some work that Dan Mazurek from Langley had done, but I was really adamant about developing a good reference science program. And this doesn't necessarily mean it's the exact science program we do with humans, but we wanted it to be representative so that we could trade off different architectural options against this science program. And I'm not going to read all this or bore you, but we came up with 11 different sites, and there were inputs from all the space guys, planetary scientist Paul Abel, and I think Dan made inputs to this early on, and others. And so we had these 11 sites, and then within each site, we actually had 5 sub-sites. And these were like a kilometer in diameter. And then within each sub-site, we have a standard circuit that we did. And we've been doing this all the way back to the asteroid work we did, where the standard circuit is performed across a 100-meter area of geological interest. And in this circuit, we actually do a bunch of standard tasks that involve 2 float samples, a soil sample, a core sample, a hammer chip sample, and an instrument deploy task. And we've kind of evolved this, but these are representative, and they wouldn't necessarily be the exact task you do, but it's a standard approach that we can use to look at the relative benefit of different architectures. And from this, we actually developed 16 detailed EVA timelines, at the level of detail that we would do a station assembly mission. And so a lot of work went into that. So that was our reference science program. And then we took those tasks and we went through and did a task decomposition, looking at the forces, the torques, the translation accuracies, the manipulation requirements, and so forth. And from the task decomposition, we developed these functional requirements And then we had brainstorming sessions that included work with the Rhode Island Institute of Design. It came up with all these different work system concepts. And I'm not going to bore you with all of them, but we had many, many. And I wanted to start with a clean slate and not assume one thing or another. But through that process, we actually down selected to 3 basic categories. One would be a jetpack only, and then there would be another jetpack with multiple carriers and samples that would basically accompany EVA astronauts to jetpacks on an EVA. To the right of that is an unpressurized excursion vehicle. It's like a sort of Segway type vehicle. You have hop legs and RCS prop. It would carry your tools. Might not have anchoring. We'll talk about it. It had light, additional power. And then the last stop, pressurized excursion, which we did a week or 2 in a pressurized vehicle. We had a couple of different classes of that. So we started out thinking, let's just go with jetpacks. That's the cheapest thing to do, and if we can make that work, that's low cost and so forth. But the published escape velocity of Phobos is 11.4 meters per second. But when we got our smart guys from GNC looking at this with Copernicus, we found that there's some very low energy escape paths at the sub and anti-Mars points of 2.4 or 2.84 meters per second. So you could almost jump off at these locations. And then, as I mentioned in the intro, what we would really use on the real mission, and we wrote a bunch of them, and the ones that were sort of relevant is that for Constellation, we actually had a requirement to return to a radiation shelter within 20 minutes. So we did some analysis that if I was on a jetpack and I needed to return, to the hab within 20 minutes at different speeds, and we normally like to fly the safer at 0.5 meters per second or less, and this is because if the suit would contact something, you can do damage if you're faster than that. But at 0.5 meters per second, if I want to get back in less than 20 minutes, I can only go out about 500 meters. As I speed up, if I wanted to go, say, 5 kilometers, I have to go at 5 meters per second, and that can get me back. But now, I'm into this situation where if I'm with open loop controls, it's really scary. Navigation on Phobos is anything but intuitive. If you retrograde relative to Phobos, it's actually retrograde relative to Mars, so it increases your orbiting. And next thing you know, he's a little higher than the star.
You are no longer needed.
Higher. And before you know it, speed path. So kind of early on, we decided that we really don't want to do jetpack work itself without adding all the ESP that we target. So we kind of ruled out jetpack as a thing. Unpressurized excursion class pressurized from a space exploration lab with RTS sled and for a hop. Looked at app-derived answers and so forth. And this next slide actually shows the space exploration vehicle. This is from the RATS FY12 work that we did, where we actually spent at Itokawa flying very detailed trajectories. And the whole OpsCon is that you've got a pilot inside this space exploration vehicle, and then a second astronaut out on a positioning arm and doing the sampling task. And it's really a nice way to work because you've got all these sensors on the vehicle itself. You've got great windows. The person in the habitat is actually serving as a Capcom with the ground, and then coordinating with the EVA crew. And like I said, one guy is on an arm outside of the vehicle, And we actually worked, but if you see this little yellow and black stripe thing, I call it the thing. We basically would fly into the asteroid, and there is a RCS mode where it's on the stinger. RCS system serve about 10 pounds on that stinger. So you push against the asteroid. Between that stabilization or the inertial mass of the vehicle, we were stable enough to be a sample. And want to see relocate, we do not want to fire full RCS to that whole asteroid. So the stinger is actually linked after, and it kicks off like a pogo stick, not the asteroid, at which point you're clear to fire RCS.
Michael? Excuse me, Michael? We're having trouble with your telecom line. It's breaking up a lot. Could you disconnect and try reconnecting?
Yes, okay, I'll do that. I'll be right back with you.
Okay, and everybody else, please stand by.
Okay, back to you.
Okay, go ahead and try.
That's it, 1, 2, 3.
Okay, you can go ahead and begin.
Okay, did we miss several slides? Should I back up or just keep going? Should I?
The group here says yes, back up a couple of them because you're broken up pretty bad last few minutes.
So I'll back up to the PEV options. So you probably know about why we want to do jetpacks, because we didn't want to end up on an escape trajectory running out of oxygen. And then we looked at these pressurized excursion vehicles that range from the so-called space exploration vehicle with an RCS sled and a hopper to various MAV-derived taxi-lander configurations. And this slide just shows what it's like to work from a space exploration vehicle. This is from Desert Rats in FY12, where we did a 2-week mission at Itokawa. And the ops concept here is you've got this pressurized excursion vehicle. There's a pilot on the inside, another astronaut on the outside on a positioning arm doing the sampling and geological work. And then there's another crew member back in the habitat that is serving as the capsule communicator with the science team on the ground. And this just shows the results of the STEM. I was talking about this called the Stinger. It's the black and white stripe. And the idea was you would fly into the asteroid. The Stinger has a string gauge that controlled to the RCS system, so you could push up against the asteroid with constant force of about 10 pounds. Between that and inertial mass of the vehicle, that's not good for the astronaut to the sample cap. And then when you want to leave, the Stinger actually is a linear actuator, so push off so you don't have to fire 4 jets at the asteroid. And this is part of a modular cabin approach that we've been looking at, where you have a core cabin, an eclipse system that can then be kitted with different mobility to be a lander or a planetary probe, the chat, or taxi over by Mars. The idea is to sort of invest in this one mod cabinet. So those were the options that we looked at, and then, are you hearing me okay now?
No, you were dropping out real badly up until you asked if we could hear you.
Um, should I call you back? Alpha, if that's better.
What line is he using?
You're using a landline right now?
Yeah, I'm on a landline.
I'm just amazed that it's dropping out so much. It might be how you're holding the phone and the orientation to your voice. Why don't you continue on that, but make sure that you've got it basically where you were when you asked the question, "Can we hear you?" And because we heard that just fine.
It's right in my mouth. Can you hear this now?
Yeah, that sounds good.
Well, that's do you want me to go over all that again, or?
No, let's move forward.
Okay. So that just gives you a sense of the range of work systems that we looked at, and then we developed this integrated model that combined Copernicus estimates for the delta V, for the DRO, and the region-to-region surface gross translations. Zach Cruz and his team actually built a very high-fidelity physics sim of Phobos. We used that system to look at the delta V for the short intra-site translations. We combined this with the logistics calculator that the Langley campaign team uses. Our masses for the habitats came from Matt Simon and Dave Reeves at Langley, who are doing all the habitat work for the HAT team. Our detailed EVA timelines were done by me and Steve Chappell, and again at the level of sort of a space station assembly task. The high Mars orbit to Phobos taxi estimates were based on work from Tara Posgrove at Langley. And so this integrated model actually generates mission level estimates and comparisons of 70 plus figures of merit, including system masses, logistics, crew time, EVA overhead, EVA productivity, and propellants. So a very, very detailed model. And this slide basically shows the results of years of work at the different options we looked at. And are you still hearing me okay?
You just started to drop out a little bit right there.
I right up against my mouth. Are you hearing me okay now?
You're still give me a count and let me check.
Test 1, 2, 3, 4. 1, 2, 3, 4.
Well, there you're good.
You know what I can do? I can call you on my cell. The problem with my phone. It's still quiet.
Okay, let's go ahead and try that then. So call back on your cell, and we'll just stand by for a few minutes.
But call it myself. Yeah, bye. Okay, with you on my cell. Does that sound any better?
Yeah, I think we're okay now.
So this wire my top. Okay, so that's shown here. What I was about to say is that this slide basically summarizes your work all the top that we looked at. And the first option we looked at was no chip point match. And then we would actually tax those high Mars orbit a pressurized surge vehicle with service module with 2 crew for 50 days, max to high Mars orbit in 35 tons. We're able to achieve 100% of the science site with just this one vehicle in days. There's only a 3% reduction in the radiation dose. And then the only Phobos tip cells here that aren't large surface forwarders are RCS flex optical hoppers. The next stop would actually have one would be pre-deployed in red. That says 11 kilograms of stage mass, and the crew would taxi over 4 crew again for 50 days, and cut down the mass at the high point. And again, we achieved 100% science, not much Richardson goes, had the advantage of redundancy of having 2 Ds and 4 crews that would involve international, get some more content and so forth. Okay, then the next option was to use 2 PEVs and a CRO path. With pre-deployed a habitat to a 1 kilometer CRO around Phobos along the, and then we pass it over and do a 500-day mission. And for this, we get 100% of science done, not much based on the radiation because we're a CRO. The next step we looked at was one is attacked and then a surface habitat, the fixed habitat. And with that, again, 4 crew for 500 days, or even 1,000 days session, pre-stage D, RCS sled, and the habitat Phobos on a controlled system taxed over. And this results in science, there's redundancy and it's radiation stuff. And then we were asked, what is the absolute minimum? So what's minimal lander taxi where we come over in the mouth, Apollo style, 2 crew with land, and basically depress cabin, that site, then have to spend hours cleaning ourselves up to come back in, and so forth. And with that, we didn't get we basically 20% of the science sites done, and not radiation protection. Now, the last option that's sort of a minimal tax getting a mobile cab. I'll talk about more later. That's on path that actually moves all around the surface. Then you have to go get from the cabin. It showed some metrics of the mass for all cases that are minimal pre-deployment, have a lot less mass. Shows the function duration. I'm not going to bore you with all the details. The lowest mass case was the minimalist action lander, which came in under 20 tons. And then this just shows the percent of the reference science content completed with the different options. And most of the apps we got the science done. In the case with the minimal lander taxi, where we actually just landed at one site. You did what science done, but as Greg pointed out, is that it's still better than the high Mars orbit mission only, because you got to Phobos, you landed there, you got the sample, and maybe it's not that bad. Okay, moving on. Did a fair amount of work with looking at hoppers, try to exploit the low gravity level of Phobos. This basically a L here, but we would have this SEV cabin. It would have an RCS sled that also had a control. We actually had CMGs as well. Then we had these 6-stop hopper legs that have a really long stroke, so you can actually stroke for about 1.5 meters. It was the hopper weighed 1,461 kilograms, and basically would hop around on Phobos to exploit the gravity level. It turns out we did the numbers, and the energetic to do 135 kilometers per verse was like 10 kilowatt hours. And so it's really a very effective way to move around Phobos. And this plot basically shows the total mass against the number of science regions explored. And the red line is mass hopper, and then the green and blue top mass to go from region to region. And blue line basically where we're more efficient, your planning, and the big line when you just want to has to come back out. But you can see here that the hopper paid for itself in similar 5 regions. And the other advantage of the hopper, once the crew lab, they just asset behind around control that science, information. So we like the hop. This slide shows the mobile app concept. Again, it's on app play. And the left there for the boom and work off the boom. Then that's one so far. So talk about excursions on jetpack while heavy. Have to worry about a lot of this art one sisters. Very interesting concept.
Mike, this is Dan again. You're still breaking up kind of badly. Yeah, I think you need to watch where your mouth is relative to the mic of your cell phone.
That makes me think that it's more in the wiring on your side. I don't see that helps. Okay, here I am on I've heard a lot of feedback.
Okay, I'm going to mute right now and see how you, let me know how you're doing. Why don't you go ahead and continue.
That's a tremendous amount of feedback. Hello?
We're still here. You're getting feedback out of your computer?
You're not. For me, it's like a lot of static feedback.
Yeah, stand by. Let's get Ricky into this conversation.
I'm here. I'm trying to see if I can isolate any of where that static is coming from. Let me reestablish the connection from the Polycom to the telecom line. Stand by.
Thanks, Ricky.
Close. Now, go. Please hold while I confirm passcode. 0, 1, 8, 0, 1. Not a passcode. I confirm. Please write passcode. Please hold while I confirm passcode. Thank you. The passcode confirmed. When you hear the tone, you will be the third person to join.
This is Ricky. I was still getting the static call the time where I was disconnected from the telecom line. I'm not sure exactly where that static is coming from.
Can you hear me clearly over the static?
Right now I can.
Okay. I'm going to press the static if you guys can handle that.
I'd say go ahead.
Okay. Should I back up or are we still taking? I was talking about the mobile hab.
Let's go ahead where you are.
So this is mobile hab. I just talked about that. With the mobile hab, we wanted to look at what airlock protocol would be to go out and do a spacewalk. And because Phobos is basically microgravity, we would use what we now use on space station as the in-suit light exercise pre-brief protocol in order to protect against decompression sickness. And this just kind of shows the timeline. The out protocol actually with suit donning and all of that overhead takes 3 hours and 39 minutes. We assumed a 5-minute airlock egress. We assumed 15 minutes for jetpack donning and checkout, and then another 15 minutes to doff and recharge the jetpack, and then I think conservatively assume 20 minutes for cleaning up the suits, and then another 10 minutes for airlock ingress. And so we ended up with an overhead of 4 hours and 44 minutes, and on a 6.5-hour EVA like we do on space station, the so-called work efficiency index, which is the EVA time divided by the overhead time, is a very low 1.37. If we had suit ports on the HAB or in a space exploration vehicle with the exploration atmosphere that's 8.2 psi, 34% oxygen, this is what the timeline looks like. So it's 20 minutes for suit port egress, the same 15 minutes to do your jetpack donning and checkout, 15 minutes to doff it and recharge. Because the suits are on suit ports and you don't have to clean because you're not coming in, that would be sort of a minimal 5 minutes, and then the suit port ingress is 10 minutes. And so in this case, because of the exploration atmosphere, our overhead time is only an hour and 5 minutes, and you get a work efficiency index of almost 5 times more than the 14.7 approach. You all still hear me okay?
Yes.
Okay, good. So back to the mobile hab, and so the idea was that they would use the athlete, which I think most of you are familiar with, that the JPL team had come up with, and we would basically have a mobile habitat that would use RCS thrusters for repositioning from region to region, and then once we got to the region, we would actually ambulate on the 6-leg athlete, and do our standard tasks of the circuit that I described earlier. And then we talked about these triangular booms, and we actually evaluated the JPL microspine anchoring technology, where you could maybe locally react forces to a large rock and things like that. So the idea is these booms would be deployed from the HAB. What I don't show here, but I'll talk about more later, is that there's booms on both sides of the hab, and so they actually serve as outriggers that give you a lot of stability. And then we can either work off a portable foot restraint. Keep bumping this phone. A portable foot restraint, or with what's called a body restraint tether that would slide along the boom. And I'll talk about it more later. We actually built this and tested it at NEMO 20 last year. So this is the idea. You basically have about a 100-foot radius. And as I mentioned earlier, we would be on jetpacks with a tether. And so if we wanted to go just a little bit further, we could do that. So that's kind of where we ended up. And then we had a big down select. And these are the options that I went over earlier. And we basically, we like the mobile hab because the hab taxi actually came and docked to the hab. And so the crew had to aboard the taxi there, and, you know, everything was all together. But we started thinking about it more, and the trackability of that's not so good. You wouldn't want to take that, you know, into a crater and so forth. And so for a number of reasons, we down select to the stop where we have pre-full 6 half, not mobile hab on half, mobile at 1. And we'd also pre-full specialized full the Mars half and select tax of high bar for both tabs. And we had a couple different ops concepts there. I'm just going to step through these. So option 1 here is the habitat and PEV are pre-deployed to Phobos. The PEV would insert into a 20-kilometer DRO orbit. The hab would land at landing site 1, and this would be sort of a prerequisite for the crew Mars TMI burn. So, you know, you're going to Phobos, you want to make sure that your hab has landed successfully on Phobos. And so then the crew would arrive in the Mars transit vehicle, and then they would taxi over to the PEV and do a rendezvous and docking in 20-kilometer DRO orbit. And then the PEV would then deorbit and fly down and dock to the hab. And then we would do a check out of the hab systems and hardware. We'd do a 2-week period to demonstrate the functionality. That is all with close proximity to the hab. And then we begin our exploration, keeping the PEV within some region of hab at scale. We could either walk back, and I'll talk about that more later, or have the hab over and execute the At about halfway through the mission, we would actually relocate the hab again to minimize the distance of dispersion hab, as well as power and lighting requirements again. And once that was done, the crew would transfer to the PEV, and then they would do a burn to the 20-kilometer DRO orbit and mate with the MAV that was parked in that orbit, and then transfer back over to the Mars transit vehicle to come home. And so that's scenario 1. Our MAV team actually wanted us to look at an option where we'd actually bring the MAV all the way down to the hab. And so in this scenario, the hab and PEV are pre-deployed to Phobos. The hab with the PEV attached to it would actually land at landing site 1. The crew would arrive in high Mars orbit with the Mars transit vehicle, and then they would take the taxi all the way from high Mars orbit all the way down to the hab and dock with the pre-deployed hab. And then the rest of the mission looks pretty much the same. And then when you want to go home, you actually just get into the MAV and do your burn and go back to high Mars orbit. So those are the 2 basic options or ops counts we looked at. This is kind of back to what that one that have over have at month here next step and have steps which will float out have and stop that have that's one have from have one dot environment what block at so look at app so not spell out but some app basically have
Dropping out again pretty badly.
okay. Okay. So Ricky,
Yeah, I'm here.
um, you can talk about, I'm going to that
You're breaking up there. I wasn't understand.
Get back and but that's still,
Yes, I am.
I don't know what, still him help on what, yeah.
Would you like to try a different telecom line altogether? It's got just same dial number, but a different passcode. Would you like to try a different telecom number that has the same dial-in number, but with just a different passcode?
Okay, if you send me that, I'll
Okay, I'll send it right to you.
Welcome to the NASA. Please hold while I confirm your passcode. Thank you. Your passcode is confirmed. When you hear the tone, you will be the second person to join.
Okay, Michael, is that any better? It sounds the same. I think I'm still getting static.
I'm with you, the chat, me.
Go ahead.
Okay, testing 1, 2, 3. Can you hear me?
Yes, looks like the static has gone away. It looks like the static I was getting is coming from UCF.
Okay. That sounds good. I'm not hearing you very loud. Are you hearing me at the right level?
Yeah, you're coming in loud and clear.
Okay, excellent. Is everybody still online?
Dan, can you go ahead and reconnect your Polycom? Yeah, UCF, please reconnect.
So, Ricky, just let me know when you want me to start again.
Stand by. We're reconnecting with Central Florida.
Okay.
Okay, Dan, can you hear me okay? Okay, how about now? You should be able to hear me okay. So I accidentally put you in the wrong room, but you should be okay now.
Okay, I hear you great, Ricky, and I'm not hearing the static. Is Dan and the rest of the team on?
Stand by. I'm trying to reestablish that connection.
Okay.
Okay, looks like the static is coming from the UCF site. I can go ahead and mute it until the Q&A portion.
Yes.
Okay, you can go ahead and begin with your presentation. And UCF, if you have any questions, you can message directly to me in the chat window in Connect.
Okay. Again, I apologize for all the interruptions, but hopefully you followed up to now. And I was talking about the different ops cons for what we do with the MAV, and the advantages of leaving the MAV and DRO are basically that it's not subjected to environmental damage, and there's some other reasons too. The disadvantages are that the MAV taxi is remote and not available for routine inspection and or maintenance. And the abort scenario is actually more complicated because the crew would need to transfer into the PEV. The PEV would need to do a burn to insert into the DRO and then do a rendezvous and docking with the MAV taxi. So option 2, which the MAV team wanted us to look at, was basically that the HAB would land with the PEV and the crew would transfer directly from high Mars orbit in the MAV taxi, which would then deorbit and dock with the HAB. The advantages there are that the MAV taxi is available for routine inspection and maintenance. It's a simpler abort scenario. You just get the crew in the MAV and abort. It also has potential for additional habitable volume for contingencies. If you had a HAB leak or failure with 2 crew out in the PEV, the 2 crew in the HAB could bail out into the MAV, and you have redundant communications. The big disadvantage here is the risk to the MAV taxi from the Phobos surface environmental factors, significantly more complicated relocation scenarios. So if I want to relocate my HAB, I could have 2 crew in the SEV and 2 crews in the HAB, but then what do I do with my MAV? Do I relocate that with the HAB? That results in some landing stability issues. Do I just send it up, to loiter telerobotically and bring it down? It's fairly complicated. And then you also get into complicated docking scenarios. And so where we got to is that we felt like the better part of valor was to leave the MAV and DRO, but we could look at hybrid options. And after initial operations on the moon's surface, if we feel comfortable with the environmental conditions in the HAB berthing operations, then we might consider deorbiting the MAV and berthing it to the HAB, probably after the first relocation of the HAB, so we didn't have to complicate the relocation aspect. And then we might also consider using the PEV once in a while to do an excursion to DRO to check on the MAV. And it could do that on the way to a distant science site so that the delta V penalty wouldn't be that much. So that's where we left that. The other thing that we're really interested in is, could we walk back from a disabled PEV? And if we didn't have to have the HAB come and rescue us, this would really simplify our operations. And so I started thinking about this, and we did some calculations. And if a crew member applied a force, I weigh about 180 pounds. If I applied a force of 180 pounds for about 2.2 seconds, I would go 51 meters. It would take me about a little over 2 minutes. And this just shows the trajectory profile. If I was able to stroke longer and apply the force for 1 second, I would go about 1,300 meters and roughly a 10-minute time. And so it's interesting. And basically, one of the questions is, what's the maximum safe distance the PEV can be from the HAB? And looking at human-powered methods, this just is a table that shows, like with the 1 second force application, we could actually go 10 kilometers in an hour and 26 minutes. And as I started thinking about this more, you probably wouldn't want to just jump. And you'd probably translate much the same way we do on Space Station, where you get yourself moving and stay low, so you didn't waste the time going up and then coming back down. And so you just stay low and you push against the surface and work your way back to the HAB. If you were over the horizon and you couldn't see the HAB, feel free to jump up and get a visual on the HAB and then go back down to your sort of low translation mode. And then as we got close to the HAB, just deploy your jetpack's auto station keeping, auto attitude control mode, and then you climb into the HAB. And so if we could actually walk back in the suits, again, that simplifies things. So that kind of entered into our integrated timeline consideration. And this slide just kind of steps through the steps once we got there. We planned 2 days to activate and check out the HAB hardware. And then we perform either a 1.5 to 4 hour pre-breathe, depending on the suit pressure. Our exploration suit has a variable pressure regulator, so it's capable of operating at 6 psi, actually all the way up to 8.2. And so we'd be in the HAB with the crew, we'd pre-breathe, we'd egress the airlock, we'd deploy one of these outrigger booms, get a contingency sample, do a limited surface locomotion adaptation, complete the EVA, evaluate suit cleaning methods, and then we'd ingress the PEV via the suit ports. And now that crew would go out for a week in the PEV, all in close proximity to the HAB, probably 500 meters. We'd start out by doing PEV RCS handling evaluations. We'd look at our targeted burn and our GNC system that would have been developed from the Robotic Precursor. We'd evaluate the hopper. We'd look at all kinds of EVA work methods, working from the PEV arm, the outrigger. We'd verify our prop usage. And then we'd do this DTO, demonstration test objective, where we'd look at the contingency return methods. And we'd have a crew member on a tether with the PEV following back to the HAB. And we'd understand just how efficacious that method of contingency return was. And then after a week, we'd swap out the crews. And the second crew would, again, do that 1 week's training, verification kind of thing. And then after that, we'd fall into this standard pattern where for 3 weeks, we'd have all 4 crew at the HAB. The typical day would include 6 hours of maintenance, exercise, pre- and post-sleep activities, and then 6 hours available for low-latency teleops and other science. And this would be low-latency teleops of Mars surface assets and possibly Phobos precursor assets that remain from the Precursor mission. And then every 3 weeks, we would go out for a 2-week excursion with 2 crew in the PEV and 2 crew remaining in the HAB. One of the HAB crew members would serve as Capcom with the Earth Science backroom, and the other HAB crew member would be doing the maintenance, exercise, pre and post sleep, and they would swap out halfway through the day. For the crew that was in the pressurized excursion vehicle, our plan would be to do a 4-hour EVA in the morning with 1 crew member. That he would then come in for lunch, he or she would come in for lunch, and then the second crew member would go out for another 4 hours. And then after about 5 of the 11 regions, we would relocate the HAB and finish the remaining regions. So that's kind of a summary of the overall OpsCon and mission plan at Phobos. So we started looking at this a little closer in terms of the hopper and would we need to refuel. And the total prop, if we did 2 missions with all 11 sites, would be about 4,800 kilograms, not including HAB docking prop. If we use the hopper exclusively, that cuts the prop down to 258 kilograms, and we probably wouldn't have to refuel. But when we started looking at the hopping, and let me slow down and talk about this, we don't really know what the soil mechanics is on Phobos, and so we actually ran a sensitivity analysis where we were between 10 and 90% efficient. And the times that it took to go region to region could be as little as 4 hours or as much as 40 hours. And so we didn't want to waste all that time because we're actually power limited, that I'll get into later. And so we said, let's assume that we use reaction control propellant to go region to region, and then we only hop within the region. And this curve just shows where the hopper pays for itself. And if you look at the lower 2, if prop is used region to region, the break-even point for the hopper is between 9 and 14 regions. And so it's sort of just barely paying for itself under this scenario. It does offer the advantage of residual use for future missions or in-between crewed missions from the ground. Part of this consideration was the power subsystem analysis, and our ER7 guy, Zuquan Lee, did a very good study here. These are the 11 sites that we talked about in our standard science reference program. And this slide just kind of shows the seasonal effects of Phobos lighting over one Martian year. So, red is good, blue is bad. And I'm not going to play this whole thing out. Okay, so this shows the Mars sub point. The point being that there are very big seasonal and locational implications of the lighting. So the blue is bad, and you can see in some of the polar regions, it's not very much lighting. And so that's a big consideration for our ops planning. So this slows, going back, our notional landing site 1, landing site 2. You can see the numbers of the 11 different regions of scientific interest all laid out on this Mercator projection. And we did a very detailed analysis of the power. And the assumption is that we're either going to pre-deploy the habitat with a ChemSep hybrid system, which actually has 435 kilowatt arrays at 1 AU, or we pre-deploy it with a SEP only, which only has 150 kilowatt arrays at 1 AU. And we looked at an average power load of 10 and 15 kilowatts. We assumed 30% solar array efficiency, and looked at between 100 and 47 and 331 square meters. And this just shows the design driving case, but even the 150 kilowatt SEP arrays, if they're solar tracking, this shows all the sites, and we're well within the power that we need to keep the HAB happy across the Martian year at each of the 11 regions. So there's really no issue with power to the HAB. And then we looked at the PEV excursions, and we initially looked at sort of 3 kilowatt average load, which is actually quite high, and that was kind of ugly. And so we basically assumed that while we're operating, we'd be at 3 kilowatts, but when we power down, when we're not operating, we can go down to 1 kilowatt. And that worked out to a 1.67 kilowatt average. And then assuming 30% solar array efficiency, 80% battery discharge, this just shows the red dotted line is the solar arrays, the power we get. And we looked at all 11 sites. And you can see that there are some sites and some times of the year that you can't go with the PEV. And there are other sites that are fine all the time. And so basically this drove a sequencing of which sites we go to as a function of time of the year. And we were able to show that we would be fine. We wouldn't have the ability to go to any site at any time, but if we sequenced them appropriately, it would be possible to do these PV excursions to all 11 sites. And this is just more of that. So the bottom line is, this is what the solar arrays would look like if we did a fixed array and then the solar tracking. And on the left you see sort of an Orion-style circular array that looks fairly reasonable. In the middle is what's called a ROSA array that we worked with Glenn on and actually did integrate those to the SEV in an experiment a few years ago. And so the solar arrays look pretty reasonable. And the idea is that they would be deployable and retractable because we wouldn't want to translate with them and risk, hitting rocks or geological formations. So they would be retracted during the hops and the site-to-site translation, and then once you were stable on the ground, you would actually deploy them and generate the power. Now, another thing that we looked at that I've been kind of researching the last 6 months is this new technology called a nano flow cell. And it's kind of interesting. There's actually a sports car that you can buy in Europe for $2 million that runs on seawater or salt water. And the way this thing works, without going into great detail, it's like a very simple fuel cell, but instead of using oxygen and hydrogen, it basically just has water with nanophase salts. And there's 2 tanks. One has positive charge, one has a negative charge. They combined in a half-cell reaction that generates power in neutral water. And it turns out that this nanophase salt has a specific energy of 600 watt-hours per kilogram, which is a lot more than we're getting out of lithium-ion batteries. It's simpler and safer than conventional fuel cells. There's no risk of explosion. The electrolyte could actually be refueled, so you could pull in and pump out the neutral fluid and pump in the charged fluid. And it actually charges faster than recharging lithium-ion batteries. And then, interestingly, the PEV, if you know about it, we designed it where it has 500 pounds of water in the ceiling for radiation protection. And then we actually use that water as a fusible heat sink to reject our peak heat loads. And there's a passive radiator on the roof that deals with the average heat rejection. But when you have peak loads that are typically 3 or 4 times the average, it just melts to ice. But from our thermal analysis, we really don't need any more than 40 pounds of ice at any one time. So we actually have the potential to use this water as a fluid for the electrolyte for the nano-flow battery, as well as the energy source for the nano-flow cell and thermal control and SPE protection. With our existing 500 pounds of water, that would provide about 3.5 days of energy, and then we could add actually more water and easily get to where we could do 7-day exploration excursions with no solar arrays at all. So that's something we're looking into for the future. Okay, this next few slides deals with the HAB docking analysis. And I'm not going to bore you with reading all of this, but we basically looked at the dynamics of docking the PEV to the HAB. And this slide here shows the static stability against ground slope angle. And we're basically stable with the PEV on the HAB from about minus 20 degrees to plus 20 degrees. And that's without any outriggers. If we add the 25-foot outrigger, we're stable from minus 30 to plus 30. And then this looks at basically the tilt angle that you would have as you docked at different velocities. And so one of the things that that concerned me with docking is that because of the gravity, as you come in to dock, you're going slower and slower, so your velocity vector slows down, and the gravity has a bigger effect. So you're constantly having to fire up pulses to keep at the right level, and any reaction control system is going to have some cross-coupling. So you really risk, having a very difficult piloting task and possibly having a missed approach. And so if you hit at these different velocities, this shows the tilt angle with the ground of the hab, which can range from, like 0.1 degree up to almost a half a degree. And then this is the settling time, which can range from 5 seconds to 20 seconds. And so as we started thinking about that, it's like if I come in and I'm having this very challenging piloting task to fire up pulses, and then I have cross-coupling, and I have a missed approach, I've got a pretty ugly dynamic situation here. And so we finally decided, rather than beating that horse to death, is that we just burst. And this basically shows that we would be in the SCV, we'd have an auto attitude hold, so we come in proximity to the hab, and then with the positioning arm, we'd actually grapple a grappling fixture, and then once that was grappled, we would burst the PEV, and that just seemed like a much more straightforward way to go. Okay, moving on. The other big question we had is, do we have to anchor to Phobos? And if we did, that would be ugly because there's not much gravity there, and even with conventional auger and so forth, you only get the anchoring forces that are proportional to the mass of the regolith plus any electrostatic surface phenomena. But so we did this analysis with a 6-foot astronaut on a 10-foot positioning arm, and we had this idea of having outriggers that we would deploy. And we looked at force application up to 45 pounds of force. And this slide just shows an example with 20 pounds of force applied. In the top curve, we would see a tilt angle of about 10 degrees. The next plot shows an astronaut can remain in contact with the surface for about 7 seconds with a 20-pound force before its 2-foot arm reach is exceeded. You would actually lift a distance of 10 feet off the surface, and it would take you about 60 seconds round trip to resettle. Over to the right here, we've shown that the minimum force to tilt the 7-ton PEV would be 4 to 8 pounds force, depending on where you are on the arm. And it would take up to 80 pounds to topple it. So it turns out we've done some preliminary investigation of the forces associated with a lot of the sampling tasks, and the majority are fairly low force, with the exception of core drilling. And if we wanted to do the core drilling, then we would have the RCS system on the PEV activated, so it would basically fire up jets to null those forces. So we got ourselves reasonably convinced that we really don't have to anchor, and that's a big one because we don't really know how you would do that or how effective it would be. So we talked about the outriggers. We actually built a pretty high fidelity version of this, which you see in these slides. And just last summer we did a test at the Nemo 20 mission, and this video just kind of overviews some of those operations. We tried to weigh it out about right, but the dynamics aren't really correct underwater. But so this just shows the outrigger being deployed. It actually has feet on it that come in contact with the surface, and then you're going to see the crew deploy what we call the hypotenuse, which then stabilizes the outrigger. And so now your load path is basically, a lot of it is into the ground and then back to the vehicle. On this outrigger, we actually have foot restraints and the ability to attach with the so-called body restraint tether. Here we're showing just a manual yaw method using a rope. And so this is what it looks like. The rope was just a low-cost way, whether in the real world we'd have mechanical actuators, electromechanical actuators, so that would make it a lot better. Now here you can see this sliding tool stanchion, and the crew attaches their sampling tools to that and then gets into a PFR and or works off a body restraint tether. These are some new tools that we developed for sampling on Phobos and low gravity bodies. And it turned out that the outrigger provided pretty good stability, and we think that offers a lot of advantages on Phobos in terms of avoiding the need to anchor. I'm going to go ahead and stop this because we're running a little bit late. I'm not going to bore you with this, but basically we have this 10-point Likert scale about how acceptable the outrigger was. 1s and 2s are no improvements necessary, all the way up to 9s and 10s. And with respect to the stability provided, it was totally acceptable from a PFR and from the body restraint tether. So we think this is a good method of actually operating and providing EVA restraint for Phobos operations. So pulling the whole picture together, this is our master or MEL list of all the components, and the idea is that we deploy our habitat with this ChemSep hybrid, which actually weighs 20 tons. And so we actually have all of that mass that comes down to the Phobos surface and helps us with stabilizing the habitat. We looked at all the eclipse gases and the prop and so forth, and we end up with about 53 tons on the surface. So it's 53 tons for the fixed tab, landing legs, all the support gear, science gear, and so forth. The PEV with the hopper is about 7.5 tons. The prop we need to do 2-week excursions is 1,100 kilograms. And if we were power limited, which I don't think we are, and we had to go out and back, it would use a lot more prop, and that could be up to 5 tons of prop. And then this chart here shows actually the payload capability of the ChemSep hybrid to pre-deploy to Phobos. And you can see at the different launch dates, we have payload capability of 58 to 42 tons. And so basically, take-home point here is that our cumulative Phobos MEL is 41 to 47 tons. And our payload capability is 42 to 58 tons, depending on when we launch and how much our taxi weighs. We actually think the taxi can be less than this, but we basically close on mass for all the launch dates, and we actually have up to 10 tons of mass margin. The SEP-only delivery can only deliver up to 42 tons, and it actually takes like 6 years or something, so we've kind of ruled that out for now. So the bottom line is we've done a lot of work looking at this mission and the engineering and the timelines, and it closes well on masses, and it looks like a very credible thing to do. And then back to the initial point that I made, that we want to use Phobos as a stepping stone to Mars' surface and not as a detraction from getting to Mars' surface. In this slide, this shows items that would be evolvable from the cislunar space, like the ARM mission and so forth. But, the SEP is evolvable, the Orion, we need that. Our habitat landing system is actually based on the alternate ARM. The taxi would be based on the HAL and the PEV-derived taxi that we're working on. And then, of course, shoot ports in the exploration atmosphere. So the Phobos mission would build heavily on what we're doing in cislunar space. And then if you look at the additional items on the Phobos mission that are not Mars forward, the only things that we would have to pay for would be these landing legs, which we actually already got from the cislunar world. And then, of course, the Phobos PEV and RCS hopper sled. So there's very few items that we would need to do this Phobos mission that are not Mars forward. And we developed the whole space transportation infrastructure, all the EVA methods and so forth. So it looks like it's really not a big distraction, and it's actually very much cheaper than Mars surface. And these slides show the systems needed for a conjunction class 500-day Mars surface stay. And in addition to the developments that you need for Phobos, you've got to sort out the aeroshell. We're actually talking about the MAV being part of the taxi, so we'd have that done. You need ISRU, nuclear fission. So there's a whole bunch of other things you need for Mars surface that you don't need for Phobos. And in terms of affordability, Phobos is a step in the direction of Mars surface. It develops the transportation operations infrastructure. If we assume that SLS, Orion, and exploration suits are sunk costs, Phobos requires 7 additional developments that draw heavily on the cislunar ARM mission. Mars surface built heavily on Phobos investments, but it requires 9 more Mars surface specific developments that are basically expensive elements that are at low TRL now. Things like the MAV, the lander, the whole EDL, nuclear fission, and so forth. We're now looking at what we call Mars Diet, where we do a much simpler, shorter stay Mars surface that would not need all these developments. So the take-home point is that within an evolvable Mars campaign that starts with an ARM and cislunar infrastructure, Phobos is a viable human target that is sensible and a relatively affordable step on the way to Mars surface. It would provide meaningful science return, and actually enhance and even enable Mars surface missions via low latency robotics that could be used for landing site verification and some of the critical offloading steps and so forth to set up the infrastructure for the Mars surface mission. And this is my get off the stage video. Zach Cruz and his team did this. This is from our high fidelity Phobos sim. So there's your HAB, and then here's the PEV, which would with the hopper legs to get the delta V to get off the surface, and then use the prop to translate. And then this is one of the monoliths. And you talk about sort of science fiction movies. I mean, this is a really exotic environment. Here we are 9,000 kilometers from Mars. There it is in the background. All this interesting geology, hopper vehicles and so forth. It's really right out of a science fiction movie, and we think it would have tremendous public engagement and good science return. And if we got that close to Mars surface, we're going there. So with that, I will close. Thank you for listening, and apologize for the interruptions. And over to Dan and Ricky for questions.
Mike, this is Dan. Can you hear me okay?
No, because Ricky has.
Yeah, exactly.
Okay. I'm going to ask, I have a few questions from the audience. I'll start with Jim Head. So, Mike, is it your opinion that Phobos is on the critical path for humans to Mars?
Let me be clear that we have not, as an agency, said that. And it's not an official position. We're still looking at different architectures and options and so forth. My personal opinion is that it does a lot to enhance a Mars surface mission. And I might stop short of saying it's on the critical path, and a lot of it depends on how much funding we have. But with the way we've approached this, where we're not really wasting any money to go to Phobos, and the costs are significantly less to do that as a first step. So I would answer that question by saying I think it's a very sensible first step that develops much of the infrastructure we need to support Mars operations and detracts very little from it.
Okay. Another question. What about subsurface habitats?
That's an interesting idea. It doesn't buy you that much. You're getting a lot of your sky blocked by Phobos. The radiation protection that I showed was based on a 10-degree crater limb. If you wanted to go in a deeper crater, like at the bottom of Stickney, you get even more radiation protection. As you go subsurface, then you start affecting your communications links and things like that, and then you have to sort out, trenching the hole and in the microgravity environment of Phobos. That can be very difficult. So I think it's interesting, but probably not worth the effort to do that in terms of just the radiation protection you get, because there's a lot of complexity associated with those operations.
Okay. What kind of robotic precursor missions would be required?
Good question. And I actually have a whole pitch on that and didn't have time to get into it, but we're looking at a couple things. Our ideal mission is we pre-deploy an orbital asset that would have, your radio science and your ground penetrating radar and all those kind of standard instruments. And then we also want to have a hopper lander. And we've sized this. It's about a 270 kilogram hopper lander with 6 solar arrays. Each of the legs has instruments on it, and every time that hopper hops, you're learning something about the soil mechanics. So we'd have desk witness plates. We would hop and then look back at where we hopped from and understand, what the soil mechanics were. We would want to characterize the whole dust environment. And one of the thoughts we had is we take our best guess at what a coating that would repel the dust would be, and we'd actually have that coating on one of the feet of the hopper legs. And if it worked right and the dust wasn't adherent to it, then you know that you've got the right coating. And if it was wrong, you learned something. And so this is, it's got good science implications, but it also needs to really pave the way for the human mission. So we'd actually like to go to most of the regions that the humans plan to go to and look for hazards and understand variances in the soil mechanics and so forth. Obviously, with the orbital assets and radio science, we could do a much better characterization of the gravitational field, which would be, very important for designing the software for our GNC system and so forth. So we would love to see that. We've also looked at other options where we could deploy a bunch of CubeSats that were piggybacked on like a Mars Reconnaissance Orbiter mission and learn something with that. And then the option that we're looking at now is that for whatever reason we don't have the money to do a proper precursor mission to Phobos before the human mission. And on the Phobos diet mission, we're looking at an option where the crew goes to high Mars orbit, and then from there deploy these Phobos assets, and then the crew from high Mars orbit does low latency teleops of these Phobos assets for months, month to 6 months, and then we analyze all that data, and then we actually taxi over in the PEV and do a 3 or 4 week human excursion to Phobos. And then come back to high Mars orbit and come home. So there's a lot of options there. The last one is a little risky because you're already committed to designing all this hardware, and if you get surprised by things on Phobos, you don't have time to deal with it. So our preference would be to launch a precursor mission by 2022 so that we could support the human mission.
Okay, the next question is actually about 5 questions. Is the surface radiation of Phobos due to albedo neutrons taken into account when calculating radiation dose reductions?
Should we do this one at a time then? So the Alteris model does account for all the secondary effects. And so the answer to the question is yes, it does account for that.
Okay, the next one of the 5. Would the surface habitat provide sufficient protection against radiation?
As I showed with the Alteris model, because of the Phobos being covering a good part of the sky, it actually reduces our radiation dose for the total mission by up to 34%, depending on launch dates. And in most days, it provides at least 20% protection. So yeah, it's the Phobos itself that provides the protection, not necessarily the habitat per se. And then it turns out.
More research. Go ahead.
No, that's fine. Go ahead.
Would more research on the effect of steady low-dose radiation on human tissue from galactic cosmic rays be required to plan safe EVA times on Phobos?
So, I think we have a lot to learn about the low-dose GCR. We have animal models, and, I work with some of the radiation guys. So, yeah, there is a lot to be learned from that. And I think this is just my personal opinion, we take everything that we've learned and we do the best we can. We characterize the risk and then we go do it. I don't see that myself as a absolute showstopper. And there are also some really interesting drugs evolving that do DNA repair, and there's, Dan, I think you were maybe at one of the meetings we had about the ketogenic ester that seems to protect against cancer and so forth. So I think there's a number of countermeasures that all get combined in a multiplicative fashion to minimize the effects of that radiation dose.
Okay, I'm going to combine two. Would you consider siting the habitat in one of the grooves? And is there any information beyond the internal composition that would be required to design a subsurface habitat?
Okay, so the grooves are fascinating, and I can't wait to go there and drop down in those grooves in a jetpack. And I mean, I think those are really interesting geologically, and it offers you insights into the internal structure of Phobos that you would not have to drill to get and so forth. So, the grooves are cool. I wouldn't even think about putting a hab in the groove until we knew a whole lot more about it. You don't want the soil to have an avalanche or mudslide or whatever you want to call it. So I actually don't think he would put the hab in there. But you certainly, that's one of the areas of scientific interest that we would go to, and possibly have our robotic precursor hopper go down and pre-inspect the grooves, before we'd actually put a human down there.
Okay. Do you expect regolith adhesion to cause significant degradation to the mechanical equipment?
Those are great questions. It's probably not going to help it, but that's one of the many things we want to get from the precursor mission in terms of, the soil mechanics and the dust characteristics, so that we could design our equipment to deal with that dusty environment. And it makes the point of doing a precursor mission before you commit the human mission. We obviously have a lot of work to do for Phobos and even Mars surface with better seals that are less dust affected and so forth. And we actually have been working with Caterpillar and others to look at how they deal with some of these things. And then on top of that, we would have to design to replace key components in a maintenance program, so that we didn't get surprised and have a failure and lose our whole mission.
Okay. In your solar power or analysis, this is another dust question, was the effect of surface dust collecting on solar arrays considered?
In first analysis, it was not. But we are actually looking at that now with the dust degradation factor, and we're kind of mining some of the spirit and opportunity data. We're actually pretty fat on power for the HAB, so even if we got some degradation there, we'd be okay. With the PEV, the pressurized excursion vehicle, we're going to be deploying and retracting those arrays, and we're going to go EVA, and so we probably have a cleaning system. And that could range from a built-in cleaning system, like a three-phase electrodynamic field that could repel the dust if it had the right charge on it, to brushes and pneumatics to clean the arrays as necessary. So it certainly is a big consideration that we would have to plan for, but I think it's a solvable problem. And the worst brute force cases, you go EVA at a certain frequency and clean the arrays.
Has a similar mission architecture been constructed for a Deimos mission?
Yeah, we looked at Deimos, and I didn't have time to go into that. It's actually easier to get to in terms of a delta V. The gravity level is less, and so all these things like the outriggers and the EVA force analysis is actually more challenging on Deimos because of less gravity. Our vision would be to do a precursor mission that would have the same assets at Phobos and Deimos, so we could understand more about it. I talked about having a 10-ton margin when we closed the whole mill and so forth. And the other thought that's built into this Phobos architecture is that you could have robotic assets on Deimos that you would low latency teleoperate control from Phobos, and possibly on a subsequent Phobos mission, you could do a taxi of a crew in the PEV over to Demos for like 2 weeks. So I think there's a whole lot more we need to learn about Demos. And at first blush, just from an EVA, force analysis, and so forth, it's actually a more challenging place to work. But you know, it's definitely in the trade space. And what the scientists tell me is that we know for a fact that Phobos is interesting with the fissures and the craters. We don't know if Demos is as interesting. It might be more interesting. We just don't know as much about Demos. So they're both in the trade space, and we have looked at Demos mission and a Phobos combination Demos mission.
Cool, more to learn. How realistic is it to 3D print maintenance parts?
And that's one of the things that we're looking at. And as part of this some MAV work that my team is doing, our vision is to come up with a design reference handbook so that anything built for exploration goes to this handbook. And you know, there's a range of fasteners that you can use, and connectors, and fans, and pumps, and circuit boards, and so forth. And that would drive a certain degree of commonality. And then if we had a 3D printer and we knew that everything on that vehicle was built from this design reference handbook, then you could not have to carry all kinds of spares. You could just carry the stock and do the spares. And so I think that's probably a big part of our exploration forward strategy, because, you know, as you know, with Station, you know, we've got, you know, all kinds of logistics going there, and we're not going to have that for exploration. And if we did an exploration system the way we did Station without standardizing the tools and the parts, it would be seriously broken. So we really have to drive toward that kind of thing.
Okay, one more. Have you considered that for some places on Phobos, a small walking speed is enough to leave the surface and enter Mars orbit? I think
yeah. I talked to that early on, and maybe I was breaking up. You didn't see that, but I pointed out that at the sub and anti-Mars point, escape velocity is 2.84 meters per second, and a human can jump at about 2 meters per second. So you could almost jump off Phobos, and that's why we ruled out jetpack only, because with the jetpack and the strange orbital mechanics that you get on Phobos that are not intuitive, you could easily find yourself on an escape trajectory, you know, running out of consumables in your suit. So we really much prefer having the crew based out of a pressurized excursion vehicle that's sized for 2 weeks plus contingency. If we were going to be on jetpacks, we would be on tethers, so you couldn't reach escape velocity.
Any more questions around the table?
Yeah, I have a question. This is Esther Beltran, and we work together back in Houston. It's okay.
Yeah.
I have a question for you. The only EVA suits that we're gonna have are the porthole EVA suits, or you're gonna have other kinds of suits that are more flexible, or like the skin suit or something like that as a backup?
Right now we're working on a new suit for Station that will be exploration forward. It'll have a rear entry, variable pressure regulator, and so forth. And so that generation of suit would be available for the Phobos operations. The suit would need to be compatible with the suit ports and the exploration atmosphere. In terms of the skin-tight suits, there are challenges there. Back in the 90s, we actually built a skin-tight elastic counter-pressure glove. And by the time you put the thermal and micrometeorite protection garments over that, it's really not that much better than the Phase 6 gloves that we have. So I'm not ruling that out, but it's not in our critical path. One of the big problems with those elastic counterpressure suits is it's really hard to get into them. And the one thought I had that I've talked with David Newman about is if you put an elastic counterpressure suit on a suit port that was exposed to 8.2 psi, which is the exploration atmosphere, that would overinflate it and make the donning a lot easier. And then once you got in the suit and buttoned up the place, you could drop the pressure to 4.3. And so there might even be a hybrid option where you've got this skin-tight suit that's part of your liquid cooling garment that is a additional level of protection in case you lost gas pressure in the more conventional EVA suit.
Okay, well, Mike, thank you very much, and also thank you for persevering amongst all our technical difficulties. This wraps up our Phobos Deimos exploration seminar. And I want to thank you very much for being a great last speaker. And this really sets the stage for, I think, where we're going to go with our studies of Phobos. So thank you very much.
Thank you.
And you can hear some virtual applause from the rest of the audience. Anyway, thanks again very much, Mike.